All right, our next talk is by Sarah Jordan. Sarah has a BS in Metallurgical Engineering and an MS in Material Science and Engineering from Ohio State University and an MBA from Carnegie Mellon University. She is currently working on her PhD at the Worcester Polytechnic Institute with her dissertation focused on the Amec additive manufacturing evaporative casting technology to be discussed today. And she's product manager at Fabrisonic. Sarah, welcome to your talk. I will give the floor to you.
All right, thank you. Thank you for that intro. Share my screen. Okay, hopefully everyone can see this. All right, so today I am going to be talking about additive, I call dark horse metal additive technologies. I'm talking about two technologies, ultrasonic additive manufacturing and additive manufacturing evaporative casting. And I'm kind of throwing down the gauntlet today to talk about these processes that you may never have heard about and talk about why those processes may win and what their capabilities are. I'm not really going to talk here about my background since that was such a good introduction. So a little bit of background on what a dark horse is. If you're not familiar with that term, you may have heard the Katy Perry song, but that doesn't really make sense in this context. So a dark horse is a horse racing term. It comes from incidents where a horse might be entered at a late stage in the race and no one knows who that horse is, and yet it can come to prominence and even win in many situations. So that's why I'm calling this the dark horse technologies. Yeah. So my background is as a metallurgist.
Can you make your slides big in presentation mode?
Can you?
Presentation mode, sorry. But you may only just see your slides.
I have them on presentation on my screen. Yeah, that's what I was. Hold on a second. Let me try this again. All right, I'll try the entire screen. How about that? Because I had it in presentation mode. Is that better?
That's it. Thank you.
Okay. All right. Sorry about that. So as I said, my background is as a metallurgical engineer, and there are definitely a lot of options for metal additive manufacturing. According to the AM Power Report, they list 18. The majority of them use powder, and as previous speakers today have mentioned, laser beam powder bed fusion is kind of the most prevalent process currently. Where I work currently at Fabrisonic, we use this process here, ultrasonic welding. But I think this map is a little bit misleading because it basically only talks about processes that have solid metal as the feedstock. So if you want to consider all the processes that give metal as the output, I think the chart changes a little bit. So there are at least 25 processes that I can think of, and there may be others, but there's electrochemical additive manufacturing is also a process, and there's at least 6 options for casting. So the Amec process, which I'm going to discuss first, is based on casting. So if we talk about casting and additive, there may be more than 6 options, but options that they're pretty well established are 3D printing sand. That's been around for a while and is pretty well established as a manufacturing process. There are several processes for investment casting. You can 3D print wax. You can 3D print a polymer, and in both those cases, you burn out the wax or the polymer. There is a company I'm aware of that is 3D printing the ceramic mold itself, just printing a hollow mold, and you can use that for investment casting. You'd also use 3D printing for just making the tooling and then using casting as you normally would. But the process that I'm developing and working on for my PhD, additive manufacturing evaporative casting, is actually based on the lost foam casting process. We'll get to that details here in a second. But my point is, with all of these processes, is that there is no silver bullet. It really depends on what you're trying to do. There's all kinds of things that need balanced. There's demands on properties and material size, all of these things. And there's trade-offs that have to be considered. So there's no silver bullet. So I think it's good for people in the industry to understand the variety of processes and when they can be used and what their best applications are. So as I said, I'm currently developing this Amec process for PhD research at Worcester Polytechnic Institute. It's based on startup companies schooled. So I'll get right into it. What is this process? So essentially, we are merging fused filament fabrication with the lost foam casting process, which is a pretty small niche casting process. Essentially, we 3D print the given shape surface, we coat it in a ceramic coating, and we pack it in loose, unbonded sand. So technically, this is a type of investment casting. It's just the difference between it and traditional investment casting is that it has a very thin coating, maybe 0.003 of an inch, the thickness of your hair, and we don't have a burnout step. The molten metal itself is superheated. It's poured on the 3D print, and that then vaporizes the metal, pushes out the gas, and then we're left with a solid replica in whatever alloy we melted. So this example here, I actually obtained this print from a vendor at a previous Rapid conference, and I think she thought it was a little bit crazy when I told her that I was going to convert it to steel. But I managed to get her to give me this interesting shape. Now, why would you want to do Amec? So right now, metal printers are still fairly expensive. And because we use the polymer printer, we're actually able to do this with fairly cheap desktop printers. We even use ones as cheap as $200. Obviously, I think for those kinds of printers, the more expensive models do give you tighter tolerances, but they're adequate for what we're trying to do and show here with our initial trials. They're also cheaper because metal powder is quite expensive, but polymer filament pretty reasonable. Because we're only printing the surface, it's a significantly faster process, and in addition, there's an option to join together multiple prints. So you can have multiple printers going. Prints can be joined by a compression fit, by adhesive, or even melting. We're not limited to the typical printer envelope because we can join the prints. We don't know the upside limitations of this process at this point, but in general, lost foam, and we assume the Amec process as well, it's limited primarily by the melt furnace size, also somewhat by the flask size, but the flask, you can fabricate a bigger flask pretty easily. We have shown that features down to 0.5 millimeter or 20,000th of an inch are possible. So we're still developing this process. This is one part that we did with this process. This is an aluminum part. Is for a boat stomp grate. And to give you some perspective, this thin section, the long thin section, is about 1/8 of an inch thick. Now, we've proven this process works in a number of cast metal alloy systems, lots of trials in gray and ductile iron, a number of steels, a few trials in brass, as you can see by this Pac-Man, Ghost, and then we've also done some work starting recently proving this process out in aluminum. I don't know this for certain, but my general belief is that this process won't work for highly reactive metals that need to be done under vacuum just because they will get contaminated with the off gas from the vaporization process. So, as I said, it is an area of ongoing and future research, doing a lot of work with various materials characterization, things like microstructure, hardness, surface roughness, some of the easier to characterize things, as well as planning to do tensile testing, just The hypothesis, although it needs to be shown, is that the resulting cast product is the same as standard casting processes. So these are some areas that we're working on, and then some additional things that we have printed. This bottom ones was done for the Air Force's Advanced Manufacturing Olympics over the summer. This is a partial picture of a spacer, and I just wanted to show this because it shows an example of the overhang capabilities, because we can bridge a decent distance with fused filament fabrication polymers. I think we've done up to about 1.25 inches. So those are some of the capabilities of the Amec process, which is, as I said, is very much in its infancy and in development. But if you want more information on this, give me a just email me at my student email, and I will be happy to discuss it further. So I'm going to kind of completely change gears here and talk different, what I consider dark horse metal additive process that you may not be particularly familiar with, and that is ultrasonic additive manufacturing, or UAM. Now, this process is quite different from what I just discussed because it doesn't involve melding at all. It's a solid state process. We have some unique capabilities here, in particular with regards to producing complex internal geometries. We do a lot of work with heat exchangers and waveguides. We do a lot of work as well, because it's a solid state, low temperature process. We do a lot of work with sensors and embedding various electronics. As you see here, we have embedded thermocouples. This picture in the middle with the little red dot has embedded a fiber optic cable, and this red light is being shown down the cable. And then, as you see here, electronics have been embedded that you can copy information back and forth to a thumb drive as demonstration parts. Another benefit of the low temperature aspect of UAM is that it allows us to join dissimilar metals in such a way that they don't melt together, because when metals melt together, they tend to form a intermetallic that's basically a mixture of the two metals, and has inferior properties typically to both of the parent metals. So in the case of UAM, we're able to join together and fully metallically bond the different metals without having those intermetallics. So these are many examples of different metals that we've done for various applications. We do a lot of work with aluminum and coppers, but all kinds of things have been joined and made into various structures. We also do work with embedding various kinds of ceramics. In this case here, we have embedded alumina, which is ceramic high strength within aluminum in such a way that it pretty much behaves similar to rebar, and it can be used as a strengthening mechanism in specially selected places. So you don't have to have your entire part thicker or strengthened. You can just do that where the design needs it. So I've kind of talked a little bit what ultrasonic additive can do. You may be wondering, well, how does this work? If you're familiar with ultrasonic welding at all, that it's pretty much using that process to join layer upon layer and build up material. We pretty much use sound and vibrate this, what we call the horn or the sonotrode, back and forth across the metal that removes the oxide layer that's on metal on Earth. And then there's two surfaces of free electron metal, and they try to grab the closest metal atoms they can, and it ends up welding itself together. This is a low temperature process in general. Depends on the metal how hot it gets. For aluminum, it's typically under 200 degrees Fahrenheit, but kind of depends on the details of the metal. So I'm going to show you just part of a quick video here, just to give you some idea of what this UAM process looks like. So this is our largest machine that we offer. That machine is 6 by 6 by 3 feet working envelope, so pretty good size. We start out by milling a base plate just so we have a nice, clean, flat surface to be able to lay down the material. And depending on what we're doing, we may embed, if we're going to be embedding things, not always, but typically we machine pockets for the device, whether it's a sensor or electronic, to go into. And then we just run this sonotrode across the surface. It does the ultrasonic process and lays down material. Here they're embedding some additional sensors and then laying down more material and kind of go back and forth to build it up. So we kind of, as you may notice, this is a hybrid process actually, because it's built on a CNC platform and has both machining as well as the additive stuff. So now they're doing some printing of copper on here. So I think I'll stop the video there. But there are other videos on YouTube if you're interested in seeing more details of that process. Now, oops, sorry about that. So why UAM? So I think it's been mentioned in some of the other talks I've been at today that there are issues of safety when you're doing powder. There's also issues with melting, of course, with safety. So the fact that this is foil, kind of the bigger risk typically is sharp things that can cut your hand, but it eliminates the risk of fire and explosions. As I mentioned with the movie, we do have a pretty large working envelope on our largest machine, and then we have 2 smaller sizes. The process is actually very fast compared to, say, most typical powder bed fusion applications. We can do up to 40 cubic inches an hour. The process also, because it doesn't use heating or melting, it does require less power, which is useful, particularly when we start talking about space applications. We can do a wide range of metal systems, both joining the same metal to itself as well as to other metals. We do a lot of work with aluminum and copper, as I said, but really there's a wide range of things that people have asked us to do for a variety of reasons. As I said, this is a hybrid process. It's built on a CNC platform. So with respect to the internal geometry, those are machined, and those give us pretty much typical CNC resolution and tolerances. So some additional applications that I said, we've done a lot of work with heat exchangers and waveguides. With dissimilar metals, there's a lot of reasons people have done these things. A lot of work with replacing cladding or brazing materials, just partly because those have really long lead times, and people don't want to wait 8, 9, 10 months for those processes to happen, which is, I guess, pretty typical in the industry. We do work with material transitions, coefficient of thermal expansion matching, as well as adding specialty foils such as tantalum for radiation shielding. As I kind of discussed selective strengthening already, but we've done a lot of work with protecting sensors, embedding electronics, digital twins with our embedded sensors, and we're starting to do some work now with technology protection applications. The other thing I'm going to mention is a product that we have we call the Smart Base Plate. So we use, in this product, we actually embed a fiber optic cable in a base plate that is intended for powder-based metal additive processes. So, you know, a lot of times people will 3D print something and the very last minute it cracks or it breaks off the base plate. And this device is intended to give warning to that and to help people for process monitoring, as well as to understand what's happening as they're 3D printing in their own machines. So I will close with this quote from the Roman poet Ovid, that a horse never runs so fast as when he has other horses to catch up and outpace. Amec is a new process and is just starting to get developed. And UAM, well, it's been around for a little while, but I think it's less commonly known, and it definitely has its niches where it is the winning process for what people need in a given application. So with that, I will open things up for questions.
All right, thank you so much. And you say alumina the same way I do at work, alumina, because aluminum is a bad word and nobody wants to deal with powdered aluminum. So anyway, great talk. I've really enjoyed learning about both those technologies. If the audience has questions, we have plenty of time for that. You can put that in the Q&A tab over here next to the chat participants list. First question is, can your ultrasonic head be applied to existing CNCs?
That's a good question. At this time, no, because there's a lot of mechanical design that's required to offset the pressure and the weight of it. But we have been developing smaller versions, and I think the other thing that that's in the works that may be kind of the workaround is that we're trying to develop a more robotic system that doesn't need to be on the CNC platform at all and just can be freestanding.
Great. Is ultrasonic welding the same as ultrasonic consolidation?
Yeah, I think they did use that term at some point in the past, but basically, yeah, it's using the ultrasonic bonding to build up material.
Great. What is done for support? Is it needed? I assume that is for the ultrasonic welding technology. I guess.
Yeah, so we typically start all of the ultrasonic. I mean, I could answer it for both, I guess. But for the ultrasonic, we typically start with a base plate or, other metal object. We've actually recently done some work with doing the ultrasonic UAM process on top of powder bed fusion components. So it needs to have something that's already, good and solid, and we can get a good seal of the metal foil on top of it so that will actually bond. As far as the Amec process, it really depends on your capabilities with a 3D printer for polymers. So we typically use PLA printing, which is fairly flexible for 3D printing. You can, as I said, bridge pretty far. So you can see this is a 3D print. It's like, I don't know, 1.25 inches that you can bridge. So in that case, I try to avoid supports if you don't need it, because it's just something to remove and more work and takes more time to do that. So yeah, and I guess the other thing you can do with the Amec process is because you can join materials, you can print things in multiple pieces and put them together, and it won't impact the final metal part.
All right. This is a technical casting question, so I'm not exactly sure if this makes sense, but I'll ask it. How much superheat for the Amec process? Is there any carbon concern when using a steel product?
No, I understand the question. So we have not measured the carbon pickup. That is a good question. But we previously developed a process for doing lost foam with steel. So we assume and that's kind of kept by trade secrets. So that's something we're looking into. As far as the superheat, that depends on a lot of factors. I would say it's hotter than you would normally cast. Lost foam is typically cast hotter than normal, so it's a little bit hotter still, yeah.
Great. The question is, what is the thickness of the ceramic coating on the PLA part? I think you said it was 3,000ths of an inch. 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 3,000th
Yeah, that's typically like pretty similar to lost foam. You know, it's very thin compared to investment casting, which might be like a quarter of an inch. That's part of the time savings because investment casting has so many, like they coat it and they dry it and they coat it and like it might take a week or 2 weeks for that part of the process just because they layer it up so thick.
I guess I have a follow-up question on that. Maybe I missed it. Do you support that then with sand? Do you bury the coated part? I missed it.
Yeah, so how lost foam works is that you have this very thin layer, which, you know, if you had nothing backing up, it would collapse. But so basically, there's a process to make a fluidized bed, and you basically vibrate the sand, or we usually use ceramic beads actually, to the point that they you know, close packing efficiency, and they make it so they can't move anymore. So then when you pour the metal, they don't collapse if you've done it right.
Great. And then can you explain more how the sensors are embedded in the ultrasonic consolidation?
Yeah. So usually we actually mill a pocket and put the sensor in there. There are some cases where if it's small enough, we could run the sonotrode over it directly. But yeah, usually there's a small pocket so that it's not going to get damaged in the bonding process, because it is you know, it vibrates back and forth pretty rapidly when it has pressure applied. So if you just directly put it on top of, say, a fiber optic, it will crush that. So there's usually just a pocket made to embed the sensor, and then the material is joined as if there were no sensor there.
All right, well, that is all of our questions. We'll just take a couple minutes back, break between the talks. Thank you so much, Sarah. This is a great talk, and we look forward to networking with you later. If you want to get a hold of her, you can always use the chat. But yeah, thank you so much.
All right, thanks.